Hello everyone. So again, welcome back to the latest lecture session. So I guess we have understood the relevant terms that you would come across with respect to the redox reactions, as in what do you need to understand by oxidation reduction, and what do you need to understand when someone is referring to oxidant or reducing agent, right? Oxidant electron acceptor, reducing agent electron donor, right? And so on and so forth. And one major aspect that I guess that we understood, was that these oxidation and reduction reactions do not occur independently, right? They need to occur simultaneously, right? So that's why you always have redox reactions, right? And next, I guess we started looking at a few applications, and the one that I guess we looked at in more detail was with respect to the wastewater treatment, right? Where you have the organics, which are relatively more reduced forms, and you have the oxygen, which is the electron acceptor, right? And thus, obviously, you need an electron donor. So thus, we identified that the organic compound is the electron donor, right? And then you can have a relevant redox process to go through, yes? And I guess let's look at a few more applications and then move on to balancing redox reactions, or how to develop, let's say, these half reactions depending upon the kind of reactions that are going through, right? So let's look at a couple more aspects. So I think we talked about color, right? Color removal. We talked about taste, right? And again, I guess odor too, I guess. In general, oxidizing agents are added, I guess, depending on the kind of scenario that you look at, right? And I do know that we have also discussed AOPs, right? Where you have formation of this strong oxidizing agents, hydroxyl radical, which would want to accept an electron and then, what do we say, move to its or transform into its more stable state, which is OH minus, I guess, right? So that's what you see here, and that's why OH radical is a very strong oxidizing agent. So if you promote those conditions which can lead to formation of these hydroxyl radicals, you'll have the relevant, kinetics to be relatively faster, right? So again, let's move on and look at one particular aspect, right? I think we looked at this particular aspect earlier too, I believe, with respect to removal of arsenic, as in arsenic is present in different oxidation states, but you, I guess, let's say, want to identify in which particular form of oxidation state of arsenic would it be more easier to remove by the usual process used for arsenic removal, ion exchange or adsorption or such, right? So let's say here we are going to look at the two forms of arsenic and look at which particular form would be easier to remove based on the aspect that, or the knowledge that we are going to use ion exchange process, I guess, right? So I guess the relevant half reaction that I am going to write down, H3AsO3 plus H2O, right? And that's going to be, the half reaction is going to be, I guess, the H3AsO4, right? H3AsO4, and it's obviously going to be 2 electron transfer plus 2H plus, right? So I guess this is the relevant half reaction here, right? For arsenate, this is the form of arsenate, I guess, right? Arsenate, and this is for arsenous, I guess. Yes. So from this particular half reaction, and now I guess you want to be able to decide in which particular form would it be easier for you to remove arsenic, with ion exchange process. So here I guess we need to dig into our particular background with respect to acid-base chemistry, I guess, right? So keep in mind that ion exchange, so you want to have a relevant charge on the relevant compound that you want to remove. So how can you have charge here with respect to either arsenous or arsenate? You see that they are protonated forms here. So if you can deprotonate them, they can have the relevant, let's say, negative charge, or they can be or exist as anions in the relevant solution, right? And then you can remove them by your relevant anion exchanger or such, right? So here, let's say, what do I need now? I now obviously need the pKa values. So let's say for this there are 3 pKa values, but the relevant values for pKa1 and pKa2, we look at that, and same case here for 1, 2, and let's say even 3 in this particular case, I guess. So the values that I have are for arsenous are 9.23 and 12.10, and for arsenate they are going to be 2.24, 6.7, I think, and 11.6, right? So obviously you don't need to mug them up, you know the relevant pKa values will be, or the dissociation constants will be available in your particular standard books, I guess. So here I have the relevant aspects now. So let's look at again our, what do we say now, relevant background, and let's say for H3ASO3, let's say this is the concentration on the y-axis and pH on the x-axis. So I want to look at how will the concentration of the relevant compound change with the pH. So if I look at it for this particular case, the arsenous H3ASO3, you know from your environmental chemistry background in acid base, this is going to be the relevant, what do we say, the distribution, and this obviously is going to be the next deprotonated form AH2ASO3 minus, and the next one would be the other deprotonated form HASO3 2 minus, right? And this one is going to be your completely deprotonated form, which is going to be ASO3 3 minus, right? Again, keep in mind that we are writing it down for this particular form H3 ASO3 now. But the information we have is pK1, it seems, is 9.23, right? And pK2 is 12.1, and pK3 is obviously going to be higher than 12.1, I guess. I think 14, or God knows what it is, I guess, right? So here, what does this tell you now? At neutral pH, let's say if this is pH 7 or around pH 7 anyway, right, and all the acidic region and considerable basic region too, right, or in when it's the solution is basic too, not considerably though, and certainly in the neutral region or when the pH is around 7, what do you see now? That it's present as H3ASO3, right? And obviously, what does that mean now? It has no charge, right? So obviously, your what do we say, ion exchange process would not be feasible here. But obviously, if I look at it with respect to arsenate or H3SO4, right, the more oxidized form, arsenic here is more oxidized, I guess, right? And here it's relatively less oxidized, right? So here it's ASO3 and ASO4, thus obviously arsenic in this arsenate form is more oxidized form. And oxidation state, what would that be? +3 plus X and -6 is equal to 0, X is equal to +3. So if it's 2 electron transfer here, it's going to be +5. So oxidation state of arsenic here is +3 and here it's +5, right? And now keep in mind that if you look at the pKa values for H3ASO4, you see that the more oxidized form at neutral pH, right, around 7, will mostly be in the form of what now? H2ASO4 minus or HASO4 2 minus near the neutral pH, right, as you can see from the pKa, yes, near the pH value, right. So obviously, what will that tell you about the system now? So if you are using ion exchange process and the pH is in the neutral region, so obviously you want to have the more oxidized form of arsenic, which is what do we say, ASO4 3 minus, I guess, right, or the arsenate form, and only then, as you see in the neutral pH, will it have the charge, right? The relevant molecule will be charged, and so with your anion exchanger, right, you can then remove your particular arsenic from your particular solution. But if it's present as arsenous or H3ASO3 or with the oxidation state of +3, you saw from this particular figure, right, what do we observe here? That there is going to be no charge on the relevant compound at the neutral pH, right? Thus, you can't obviously remove it by your relevant ion exchange process. So that's one particular aspect. Obviously, I guess we need to look at both the redox chemistry and also the acid-base chemistry. So obviously, if you are, I guess the take-home message here in this case is, if you are trying to remove this particular arsenic by an ion exchange, it would be more efficient, obviously, if you have the more oxidized form, and thus you want to promote formation of arsenate rather than arsenous in your particular solution. So you want to oxidize the compound, right? Okay. So let's move on to one other example, I guess, that you might look at. So we have persulfate, right? And where do you come across this, I guess, right? Usually people might have heard of this TOC machines, total organic carbon, right? Where you measure the amount of organic carbon present. So again, the principle here is that you have a radical being formed, H2O2 minus, and I guess it forms this particular radical, right? The sulfate radical, yes. and obviously it would want to go into its more stable form, which is SO4 2 minus. So again it wants to accept an electron, so thus you are trying to form a strong oxidizing agent, and that in your TOC machine I believe is done in the presence of ultraviolet, right? So you are going to bombard the particular persulfate solution, which I guess will exhaust if people running with the TOC machine are keeping a track of it anyway, right? And you are forming these oxidizing agent, right? The sulfate anion radical, which is going to oxidize your particular solution. So again, one particular application that I wanted to talk about in that case. So obviously in disinfection again, right? So what do we try to do, or what are we trying to add in your particular disinfection? You add oxidizing agents, right, which oxidize the relevant biochemicals that would exist in solution, right? So again you add oxidizing agents again, it's again a process of electron transfer again, right? So what else can we usually look at? We want to remove iron. Let's say what's the relevant reaction? Fe2 plus goes to Fe3 plus, right? This is the relevant half reaction, and from our aqueous complex chemistry and the precipitation and dissolution chemistry, we know that Fe2 plus stays as Fe2 plus and is relatively more soluble, but Fe3 plus, as you know, either forms complexes or mostly precipitates out at most pH, right? So obviously if you want to remove iron, you can oxidize it and it will precipitate out, right? Fe, I think OH thrice the solid form, right? So obviously if you want to remove iron, you can oxidize it, right? Obviously Fe2 plus is an reducing agent because it's the electron donor here, right? So again, different aspects here. So again, what I was trying to, I guess, emphasize is that the applications for redox reactions are endless, or I guess as I speak, let's say I'm consuming, let's say, energy, let's say, and again relevant redox reactions are occurring and the relevant energy is being released and that's being consumed by me, right? So again, redox reactions are ever present and they play a huge role in your particular environmental chemistry, as in, let's say, not environmental chemistry, environmental process or environmental engineering, right? So obviously now let's say it can also be used to reduce the toxicity of this particular compounds or such. Example, chromium 6, I guess, right? In the oxidation state 6 is highly toxic, but chromium 3 is not as toxic, right? And also, as you know, or I think we looked at a brief example where chromium would precipitate out in the form of if it's in oxidation state number 3, but if it's chromium in the form of oxidation state 6, it's going to be more soluble. So again, you need to look at those aspects too. So you can either reduce the toxicity or also remove the relevant compound by reducing chromium here, right, to oxidation state of 3. So obviously here we are using this particular term oxidation state or oxidation number a lot. So let's look at what this is about. I'm sure people have looked at it, but there are a few fundamental rules or aspects that govern how to calculate these oxidation states or numbers. But what do I understand, what should I understand, let's say, about oxidation states now? First, I guess the aspect that you need to understand is this is a theoretical or hypothetical variable now, right? So it's theoretical, that's something that you need to understand now. But how would you assign these oxidation states or such? Let's say if there's a molecule, let's say, and you have covalent bonds here, and let's say they dissociate, and then hypothetical dissociation, and then if you look at the relevant charge on these particular elements after they dissociate, let's say, right, and then you can assign the oxidation number based on this hypothetical charge if these elements dissociate, right? So again, we are going to have a few rules to be able to understand this particular situation better. So obviously we are going to talk about balancing redox reactions in great detail later on, right? Yes, but obviously we need to look at a few particular rules, as in how to first calculate the oxidation number or the oxidation state, right? So let's look at a few aspects. So the first one is for a monoatomic substance, it's the oxidation number, oxidation state is equal to its electronic charge. For example, here we have, let's say, Na plus or Cl minus, let's say, right? These exist in solution. And so obviously the oxidation state of this particular or sodium here is +1, and for Cl it's -1, right? So that's pretty simple out there. Again, based on the principle of charge balance, nothing else there. But this is something that you need to understand, as in what if you have covalent bonds, let's say, right? In a covalent compound, let's say, so as we talked about, you are going to assign the oxidation state such that if the molecule dissociate, right, you are going to look at the hypothetical charge that each element would have, and then that particular charge would be the relevant oxidation state of that particular element. But how would, if dissociates, let's say, how would you calculate, or how can you estimate this hypothetical charge now? So for example, if a compound is more electronegative, right, so it will pull the electrons more towards itself rather than the other compound here. So obviously what do we have? The oxidation state of each atom is the charge remaining on the atom when each share pair of electrons is assigned completely to the more electronegative of the two atoms sharing them, right? So what this means is, let's say if you have two atoms sharing an electron, let's say, right, and sharing, right, so what does that mean? Both of them, are sharing it, right? But obviously what it means is that in this particular context, if a particular atom has more than 50% share, let's say, right, and you are going to assign all those electrons of which it has a 50% or greater than 50% share, let's say, to that particular atom, and then if you calculate the relevant charge, that's going to be your oxidation state or the oxidation number. Again, so how can we go about that, I guess? So obviously the more electronegative compound will pull the electrons more towards itself. For example, you have H2O, right? Oxygen is the more electronegative compound, right? So it theoretically has more than 50% share of each of the electrons that it shares with the hydrogen. So if I let them dissociate, let's say, right, so obviously oxygen will have -2 charge. Why is that? It has more than 50% share of both the electrons that it is sharing with the hydrogen. So that is why oxygen will end up with, let's say if I look at the hypothetical dissociation here, so oxygen will have oxidation number of -2 in this particular case. And obviously H, because it's losing its share of this electron to the oxygen, it's going to obviously have +1, and oxygen will have -2, right? Again, to refresh our understanding, I guess, right, we are going to look at that hypothetical charge that would be present on that particular atom if all the electrons of which it has greater than 50% charge share, I guess, right, greater than 50% share, if the share of that particular electron by that particular atom is greater than 50%, or in other words, if it is more electronegative, right, is assigned to that particular atom, then the relevant charge, right, the charge remaining on the atom would be the oxidation state. And one example we looked at was H2O. So oxygen is more electronegative, it has greater than 50% share of each of the electrons that it is sharing with, let's say, hydrogen, let's say. So it's going to pull these particular electrons towards itself. So thus, let's say the charge is going to be -2, the hypothetical charge, and that's why oxidation state is -2. And similarly H, I guess it has less than 50% share, so it's when we are calculating this particular oxidation state, we are losing, or H is losing its particular electron to oxygen here, and so thus obviously the charge on H would be +1, and thus the oxidation state would be +1. Again, something to keep in mind, or the relevant basics here, I guess. So obviously though, if it's particularly, if an electron is shared by two atoms of the same electronegativity, right, so it's split between them, right? If both the electrons or atoms have the same electronegativity, the share is 50% each, right? So it's split between them. So obviously, for example, if you look at O2 or N2 or such, let's say, both the oxygen atoms have the same electronegativity, so they have each have a 50% share. So obviously in that case, oxygen oxidation state would be 0 here, right, for oxygen. Thus you see that oxidation state of oxygen in O2 would be 0. Why is that? Because both the oxygen atoms, right, have the same electronegativity, obviously, and that is why the charge is split between them, or the electron pair is split between them, right? So thus obviously the oxidation state is 0, right, of oxygen in O2. But obviously in H2O it's relatively different. Why is that? Because oxygen compared to hydrogen is more electronegative, and it would have greater than 50% share of the relevant electrons. And obviously the last aspect, I guess, right? So the sum of oxidation states is equal to 0 for molecules. This is nothing but charge balance, and for ions is equal to the formal charge of the ions, as in let's say H2SO4, right? So what does this mean? Let's say this has no charge. So oxidation 2 times oxidation state of this particular hydrogen plus 1 times oxidation state of the sulfur plus 4 times oxidation state of this or oxidation number, pardon me, of this particular oxygen will be equal to 0, right? Sum of oxidation states is equal to 0 for molecules, and let's say if I look at the relevant deprotonated form SO4 2 minus, right? What does this mean? So 1 oxidation state of sulfur plus 4 times oxidation state of or oxidation number of oxygen, right, is going to be equal to the formal charge of the ion, that's equal to -2, right? Again, I guess people are well versed with this particular aspect, but I guess we need to obviously again touch upon the relevant basics. But this is one aspect I guess you need to be able to understand better when you are assigning the relevant compounds. So here obviously what is the information you need? You need to know how electronegative is a compound relative to the other, not compound, pardon me, the atom compared to the other atom it's sharing its electron with, right? So again, now we are going to look at balancing the redox reactions in greater detail. Right? So let's just try to have a summary before we go further, I guess, right? So how do you balance half reactions now, right? First, you need to be able to develop half reactions. Right? First, you want to be able to develop the half reactions, yes, and then what do you need to do now? You are going to transform them such that the number of electrons is the same, right? So the key is that you are going to transform or modify them such that the number of electrons being transferred or either let's say gained or lost in each of the half reactions is the same. And then obviously for getting the overall reaction, I guess you reverse one half reaction, right? And then to get the overall reaction you just add the half reaction, right? So I guess all these three aspects are relatively simple, but I guess again the key is that you know that electrons do not accumulate in the solution. So obviously the number of electrons being donated from a particular half reaction, right, need to be equal in number to the number of electrons being accepted in the other half reaction. So thus obviously you need to see to it such that the number of total number of electrons either being accepted or gained from each of these half reactions need to be the same, because when you reverse and sum or add the relevant half reactions, the overall reaction should not have obviously any electrons present in that particular overall reaction. So again this is relatively simple, but obviously we need to look at developing the half reactions, I guess. So let's see how to go about that. So first I guess let's understand I guess how to be able to, let's say, assign oxidation numbers now, right? So first I need to be able to determine oxidation numbers, right? So again we need to obviously determine the oxidation number or oxidation state of the relevant particular atoms, right? So obviously we looked at the relevant rules until now, right? Thus in that aspect we know that we need to identify the more or the electronegative atom, right? So let's look at some of these aspects, I guess, right? So in general I guess we know that let's say oxygen is more electronegative than hydrogen, and that was in the example. So thus with respect to H2O we know that the oxidation state for hydrogen would be +1, and for oxygen it would be -2, right? And obviously if you look at it, the sum should also be equal to 0 because there is no charge here. So that's what we see here, 2 times NH plus 2 times or 1 times oxidation state of oxygen is going to be have to be equal to 0, and you see that 2 times 1 plus minus 2, and that's equal to 0. So that's again, the relevant rule has obviously been, followed, right? So let's look at some of the other aspects, I guess. So N, as we know, oxygen, oxidation state is usually minus 2, unless obviously it is present as O2, right? Because then both the electrons, I guess, the electron pair is split between each oxygen atom. So thus there is no, there is no particular hypothetical charge when we split these two oxygen atoms. So thus oxidation state of oxygen in O2 would be 0, but in general it's going to be equal to minus 2. For H, it's usually equal to plus 1, right? Other than, unless it's in as present as H2. Again, same explanation as earlier. So Cl, some other compound that we usually come across, I guess, oxidation state is equal to minus 1, right? Unless again, obviously it's present as Cl2, right? Again, these are the usual oxidation states or numbers that we come across of usually usual atoms that we use in or come across in environmental engineering, I guess, right? So for sulfur, it's going to be equal to minus 2, as in one example is H2S, right? As in H2S. And let's say for nitrogen, right? And let's say nitrogen, it's going to be equal to minus 3, as in, for example, NH3, I guess, right? One example, I guess. So with this background and the relevant electronegative states or electronegativities of the different atoms that we looked at, oxygen, hydrogen, chloride, sulfur and nitrogen, I guess, right? So we can also now apply the relevant rule as in the sum of all the oxidation numbers or states for a neutral molecule should be 0, or if it's an ion, equal to the charge on that ion, and get the relevant oxidation states of the relevant atoms. Again, so let's going through, I guess, we are trying to again develop the half reactions, right? And in that context, we are trying to calculate the oxidation states. So for example, C6H12O6 and also C6H6, I guess. So glucose and benzene. So let's try to calculate the oxidation state of carbon in both these cases. So I guess, people can do it in relatively simpler manner, but let me write down the basic format, right? Plus 12 times oxidation number of hydrogen plus 6 times oxidation number or state of oxygen is equal to 0, right? And here it's again 6 times oxygen state of carbon plus 6 times oxygen state of hydrogen should be equal to 0. So 6 times Nc plus 12 times 1 plus 1, right, which we know from our previous knowledge, right, plus 6 times minus 2, right, is equal to 0. And here it's going to be equal to 6 times Nc plus 6 times 1 is equal to 0. So here I guess 12 and minus 12 cancel out. So Nc, oxidation state of carbon, is obviously now 0 in this particular glucose molecule, I guess, right? And here in this particular case, we see that it's going to be equal to, right, minus 1, yes? So obviously, what do you need to understand from here particular now? So we see that Nc, or oxidation state of carbon, and C6H12O6, right, is less than, or I guess should say greater than, because it's positive, I guess, oxidation state of carbon in C6H6, right? So again, what do we see now? So thus obviously we can see that carbon is more oxidized when it's in the form of glucose, but is more reduced when it's in the form of benzene, right? Again, looking at the oxidation state, that's the relative comparison that we can draw. It's again, I guess, carbon has oxidation states ranging from +4 to -4, I guess. So I guess this is the way you can calculate for the oxidation state of carbon in various particular molecules. And in this case, obviously, you see that it's carbon is more oxidized in the glucose molecule. Again, so let's look at the relevant aspects. So we are going to now develop, let's say, or balance half reactions, right? Balance half reactions, right? And for that, I need to identify the couple, as in, so what's the couple now? We are referring to those compounds or molecules, let's say, with before and after transfer of the relevant electrons, right? So for obviously we need to now look at one particular, what do we say now, example. So we are going to look at the example of reduction of chromate, let's say reduction of chromate by sulfur, right? So let's say this is the information that I have, and from here let's say I need to be able to come up with the or develop the relevant half reactions, balance them, and then get the overall reaction that would correspond to reduction of chromate by sulfur. So obviously in this case the first aspect is that I need to identify the couple. So here let's say CrO4 2 minus, more oxidized form, it's going to be reduced to Cr3 plus, okay. So that's because obviously it's reduction of chromate, and sulfur again SO4 2 minus, SO2 let's say, right, because it's initially reduced and it's more oxidized later, SO4 2 minus. So these are my couples, right. So here again we need to obviously identify the relevant couples. So here, because we know that it's reduction of chromate by sulfur, and I guess with some background you can know that CrO4 2 minus will be reduced to Cr3 plus, and SO2 will obviously cause this particular reduction while being oxidized itself to SO4 2 minus. So let's list this up and go through CrO4 2 minus and Cr3 plus, and again SO2 to SO4 2 minus, right. So obviously now I need to be able to calculate what do we say, or first identify which one is going to be oxidized or which one is going to be reduced, and write the relevant half reaction. So let's say if we do not have the background, obviously we need to be able to calculate the oxidation states, and anyway you need to calculate the oxidation states because you need to assign the electrons or the number of electrons being transferred, right. So we are going to do that. So obviously now I am going to calculate the oxidation state of chromium, right, and that I will do for CrO4 2 minus first, and then obviously for in Cr3 plus oxidation state of chromium, and same case here in SO2 oxidation state of sulfur, and again here in SO4 2 minus oxidation state of sulfur, right. So again, how do I calculate that here? I know that NCr, or oxidation state of chromium, plus 4 times oxidation state of oxygen should be equal to -2, right. So oxidation state of this plus 4 into -2 equal to -2. So we see that oxidation state of chromium in CrO4 2 minus is equal to -2 and +8. So right, it's going to be +6, right. And obviously here it's nothing but the charge on that particular what do we say, ion. So that's going to be equal to +3, right. And so here it's +6 and here it's +3. So what does that tell you now? That it's obviously more oxidized when it's in the form of CrO4 2 minus. So looking at the oxidation states, right, you see that what do we say, chromium is more oxidized when it's in the form of CrO4 2 minus compared to Cr3 plus. So that's one particular information that we have. So again here coming back to this particular case, for the sulfur, so plus 2 times of -2 is equal to 0, right. So -4, so the oxidation of sulfur here is +4, right. And in this case, what is this going to be? Plus 4 times of -2 is going to be equal to -2, right. Again, nothing but I guess I should have written this down, is equal to charge on the particular ion, that's equal to -2, and from here we know that oxidation state of oxygen in general is -2, right. It's the more electronegative compound here, and so with that I can get the relevant what do we say, oxidation state of sulfur, that's going to be equal to -2 plus 8, so that's going to be equal to +6, right. Okay. So obviously from this particular information, what do we have? That the information we have that is sulfur is is relatively more reduced in SO2 and is obviously more oxidized in what do we say, as SO4 2 minus. That you can glean from this particular oxidation state, right. Or you can also understand that here for one atom of sulfur you have 2 oxygen atoms, and here in SO4 2 minus for one atom of oxygen you have obviously 4 what do we say, atoms of oxygen, while having only a 2 negative charge, right. So obviously you can develop the intuition that it's going to be in relatively more oxidized in SO4 2- form compared to SO2, I guess, right? Anyway, or obviously we can calculate the relevant half reactions here. And then what do we need to do? We need to be able to calculate the change in half reactions, right? Not half reactions, pardon me, the change in the electrons, right? Or how do I get that? Or change in the oxidation states. So I'm going to calculate change in oxidation state for what do we say, chromium. So that, let's say I'm going to write NCr minus N as Cr3 plus and oxidation state in CrO4 2-, right? And this is nothing but going to be equal to the change in oxidation state as is equivalent to the number of electrons being transferred, right? So here it's +3 minus +6, right? So that's equal to -3 here, right? And in this particular case, the number change in, what do we say, the oxidation states, which would be equivalent to the change in or transfer of the number of electrons, I guess, right? SO2 here, right, is going to be equal to +6 minus +4, that's equal to +2, right? So this is what I have here. So the next step is going to be how to assign the electrons, right? So the next step would be obviously to assign the electrons, and in that context we calculated the change in oxidation, what do we say, oxidation states for chromium and change in oxidation states for sulfur, and I guess we looked at -3 here, and here it was +2, right? So -3 and +2 here. So obviously now I'm going to have to assign the electrons, and I know that we started out with CrO4 2-, right? CrO4 2- is going to what do we say, Cr3 plus, right? Yes, and here obviously it was with respect to SO2, right? Going to SO4 2-, right? So obviously now I need to assign the electrons. So here obviously what do we say, adding -3 here would be in effect +3 electrons here, right? So obviously how did we get this? By subtracting the oxidation state of chromium in Cr3 plus, pardon me, not the other way around, subtracting the oxidation state of chromium in CrO4 2- from Cr3 plus, right? So in effect that means I need to have -3 electrons here, or obviously +3 electrons on the left hand side, right? So I am assigning the electrons here. So here though I guess it's +2, so I am going to have +2 electrons here, right? And obviously what do we see here? Sulfur dioxide here is the reducing agent because it's donating the electrons, and that's what you see. And CrO4 2- is the oxidizing agent because it's accepting the electrons, or it itself is being reduced, right? So that's what you see here. So SO2 is the reducing agent, which is reducing CrO4 2-, right? So that's what you see here. So here we have assigned the relevant electrons, and then we need to balance the elements and charge, right? So usually I am going to balance oxygen by adding H2O, let's say, and balance charge by adding H plus, okay? And I guess that by then you should be able to see a balanced half reaction. So let's do that out here. So we have CrO4 2- plus 3 electrons goes to Cr3 plus. So what do you say, mole of chromium and chromium, so that's fine here. So chromium is balanced, I don't need to do that here. But for oxygen, I guess obviously there are 4 atoms here, right? But none here. So let's say I'll have 4 H2O out here, right? 4 H2O. So now the oxygen atoms, the stoichiometry is balanced with respect to oxygen, right? Again, as I said, to balance oxygen, the element, we are going to have to, we usually use, let's say, H2O to balance that, and that's what we did here. And let's say what else do I need to do now? The charge would not yet be balanced. Let's say now I'm going to look at also the amount of H plus or hydrogen elements. So here I have 8, right? So I'm going to balance hydrogen by adding H plus. So because here I have 8 I am going to plug in 8H plus here. So by now let's see if the charge is balanced. So minus 2, minus 3 is minus 5, and here it's plus 8. So on this left hand side, right, the charge is plus 3, and on the right hand side too, you see the net charge is plus 3. So by now we have the balanced half reaction with respect to the chromium reduction here, right. Again, how did we do that? We first saw to it that the number of elements of chromium was the same, so I don't need to balance that, but I see that there was a mismatch with respect to the number of atoms of oxygen, right. So that's why I added 4 H2O here to the right hand side, 4 atoms of oxygen here to balance out the 4 atoms of oxygen here, and then I see that now I have a mismatch with respect to hydrogen. So to balance hydrogen, I add H plus, right, 8H plus, and then I checked for charge and I saw that that's being satisfied. And now I am going to move on to this particular case here with respect to sulfur dioxide. So here I guess we need to first look at oxygen or the sulfur balance. So it's balanced with respect to sulfur, yes. So I am done with that, and now I am going to balance with respect to oxygen, let's say, right. And how do we do that? Let's say by adding H2O, right, SO4 2 minus plus 2 electrons. So here I guess I have 4 oxygen atoms, and while here I have only 2. So to balance that out, I add 2 H2O, right. So here 2 plus 2 atoms of oxygen. So 4 atoms in total on both the left hand side and the relevant right hand side, right. And now we say we balance hydrogen, and how do we do that? By adding H plus. So let's look at the relevant reaction here, SO2 plus 2 H2O, and let's say it goes to SO4 2 minus plus 2 electrons, right. And obviously there is a mismatch with respect to the hydrogen. So here I have 4 atoms and here I have none. So I am going to have to plug in plus 4H plus here on the right hand side, and then balance charge, or by now it should hopefully be balanced actually. So I am going to look at the charge here. So there is no charge here on the left hand side, and here it's 2 negative and 2 negative, 4 negative and 4 positive from H plus. So it's 0 on the left hand side and 0 on the right hand side. So it's already balanced with respect to charge. So it's SO2 plus 2 H2O, right, goes to SO4 2 minus, releasing 2 electrons and 4 hydrogen atoms, right. So these are the balanced half reactions that we have thus far, right. So I guess initially I guess I would suggest that you balance with respect stepwise, and then you can obviously graduate to balancing out in one step, I guess, right. So obviously I would suggest this particular manner, as in balancing with respect to oxygen after assigning the electrons, and then I guess balancing the hydrogen and the relevant charge, right. So again, let's have this particular half reactions here. So we are done with having the relevant half reactions, right. So but obviously now we need to be able to develop the overall reaction, right. But obviously what is the key with respect to developing the overall reaction now? That you need to be able to balance the number of electrons being gained or lost. For example, here you see for 1 mole, I guess anyway, in this half reaction there are 3 electrons being gained, but here there are only 2 electrons being gained, right. So I obviously need to be able to match the number of electrons being gained and accepted, because in the overall reaction I can't have any electrons being either accumulated or being accepted, let's say. So thus I am going to have to multiply this particular reaction by 2 and this particular reaction by 3, right. So let's try to write this down here, I guess, right. 2 CrO4 2 minus plus, I guess now it's 6 electrons, right, plus 16 H plus goes to 2 Cr3 plus 2 Cr3 plus plus 8 H2O, right. Okay, and the other half reaction I guess is obviously going to be 3SO2 plus 6 H2O, right, is going to be equal to 3SO4 2 minus plus obviously 6 electrons, right. Now you see that the number of electrons being gained and lost is the same, right, plus 12 H plus 12 H plus. So obviously to get the overall reaction I need to put, what do we say, swap the relevant half reaction, right? And if I write that down in that, or do I need to swap it here? I guess not, because the relevant half reactions are in such a way that I have the electrons being accepted on the left hand side and what do we say, donated on the right hand side. If not, obviously I need to swap it, so which is not the particular case here. So I'm going to now have my overall reaction 2CrO4 2 minus plus 3SO2 plus 6H2O plus 16H plus, right, would go to 3SO4 2 minus plus 12H plus plus 2Cr3 plus plus 8H2O, and obviously I need to now balance out with respect to H2O and such, right. So here I have 8 and 6, so in effect this would end up being 2H2O here, right, and here I have 16H plus and 12H plus, so in effect this would end up being 4H plus here, right. So this is my overall redox reaction, right, and here we have the chromium being reduced and what we say sulfur being I guess oxidized, right. So the relevant half reactions, these are the half reactions, and this is my overall redox reaction. Let's just try to identify what's happening here. So the sulfur is donating its electrons, right, and these electrons are being accepted by chromium in the form of CrO4 2 minus, and it's transforming into Cr3 plus, right. So again you can identify the relevant reducing agent here. So the reducing agent is nothing but SO2 here, because it's donating the relevant electrons, and it's donating the electrons to CrO4 2 minus, which is obviously now going to be reduced from oxidation state plus 6, which we calculated earlier, to oxidation state of plus 3, which is Cr3 plus form, I guess, right. So I guess this is a way, or once you are to be able to develop the overall redox reaction. So obviously we looked at the relevant aspects stepwise. So once you are relatively confident, you can obviously do them in one step, right. So now we are going to move on to kinetics, right. Again, we did mention that kinetics plays an important role with respect to our particular redox reactions. Why is that? Because the relevant time frames involved, right, you usually do not reach equilibrium. The kinetics are relatively slow compared to what you observe with respect to acid bases, complexes, or precipitation, not precipitation I guess, at least with respect to acid bases and complex formation. So the kinetics is relatively slow and rarely do you reach equilibrium now. So usually when we talk about redox process, you must almost always talk about the kinetics now, right. And that's what I guess we are going to discuss in the next session, and then move on to applications of what you would expect if, let's say, metastable equilibrium or equilibrium has been reached, and how to understand the system. And I guess with that I'll end today's session, and thank you.